going to make a quick run through this presentation that we went over in class. Slightly different view so I can ink it up and make some notes on here. So we started off talking about waves, and we wanted to remember that we were largely following up from our first unit on energy. And if we go back to our first unit on energy, we talked about 7 different forms of energy. And let's remember that the S was for sound and R was for radiant or radiation. And so a lot of this unit is going to be going back and just going into more detail about those 2 forms of energy. When we have a wave, what we have is we have energy being transferred from one place to another. So energy is moving. We want to remember that energy is the ability to do work. And so when we have a wave that's transferring energy, it's effectively transferring the ability to do work. We will learn further in the year that work is defined in physics as a force times a distance. So if work is being done, then neither of these numbers can be 0. So that means we have to have some kind of a force, which is a push or a pull, and we have to have something moving a certain distance. Therefore, if we have a wave, then if the wave does have energy, then that wave has the ability to basically push something and move it. And that can be something large like a boat, or it could be something really, really small on the size of, an atom or an electron or something on the subatomic scale. So in this picture that we have here, we got the boat that's being pushed up at a higher level. So it's evident in this case that the wave has energy because it has the ability to push this boat a certain distance and be able to move it. When we think about waves, we want to think about, had a little disruption there, so let's make sure I didn't lose my train of thought. All right, so I want to say, what are the things that cause waves? A couple of things. The initial source in most cases is some type of vibration. For a sound wave, that could be, my throat vibrating. It could be the strings on a musical instrument vibrating. It could be the brass on a horn vibrating. So usually we have to have some kind of vibration. And even with electromagnetic waves, normally we would think of them as originating from the vibrations of an atom or something even on the subatomic level that's going to be forcing the wave out. So when this is going to happen, we again are going to get energy transported from one place to another one. One of the big words that I pointed out on here was medium. We're going to use this word a lot, so let's make sure we understand we're not talking about the thing between a small and a large. This is the material that's going to be carrying a wave. So for example, sound needs something to travel through, and so that thing that it does travel through is called a medium. The medium could be a solid, it can be a liquid, it can be a gas. So in the picture we have over here where the hand is making a wave, in this case the water would be the medium in this one. The person with the rope down here making a wave holding onto the tree, in this case the medium would be the rope. A couple different types of waves that we will talk about. One is a mechanical wave, and it's kind of defined as it needs a medium to be able to travel through. So some waves don't need to do that. We've got pictures here of an ocean, a sound wave, and again with the rope that we have. So a medium can be a liquid. We have a lot of waves that can travel through liquid. We have a medium could be a gas, such as when you're listening to anything through the air. And a medium can even be a solid, where in this case the rope is what's actually causing the energy to go through. If we go back to sound, sound could travel through water as well. Again, that's how dolphins, whales are able to communicate. And if you've been swimming, had your head under the water, you know that you can still hear things. And we can even have sound go through a solid. If you put your head up against a wall and someone's tapping on it, again, you can hear. You might not be able to understand, but we know that sound can travel through all of these things. So we had mechanical waves. We also have electromagnetic waves. These are a little bit different. They can travel through empty space, so they do not need a medium to be able to do this. These were the R parts of Mrs. Chen. These are our radiation. A lot of y'all just kept thinking that radiant was sunlight, but sunlight is only a tiny little piece of what we consider to be radiation or electromagnetic waves. As some characteristics about these waves change, we start calling them different things. So this graphic here at the bottom shows us a number of different types of electromagnetic radiation, electromagnetic waves. Gamma, X, ultraviolet, can be also infrared, microwave, radio. Again, these can all travel through empty space and they don't need a medium. The way that they differ from one another is kind of how squished together the waves are. As you can see on the left end, the way that we would represent these is that they have really, really short waves. They're really, really close together. And as we move to the right, the waves get further and further apart as we get all the way down to radio. So the visible light is only in this tiny little area, and even within visible light, the different colors we see are going to be produced by slightly different wavelengths that we have in there. All right. When we get into mechanical waves, we can describe a couple of different types of mechanical waves, and this is going to be how did they travel across the medium that they're going through. And so a transverse wave is often represented by what looks like wave A, and a longitudinal wave by illustration B. If we go a little bit more into detail about a transverse wave, what we tend to see with a transverse wave is we want to compare the direction of the wave and the direction of the medium that it's in. So as an example, for an ocean wave, for example, if this were an ocean wave, the energy of the ocean wave is going to be moving from left to right. So in other words, if you're standing in the water, you're going to feel the energy of that hit you. However, the water itself, and if you're up against the shore, you would argue with me and say the water is actually moving towards the observer. But if we get away from the shore just a little bit, what you're going to notice is the water itself doesn't move in a left or right fashion. The water itself just kind of moves up and down. So if you were a person at the top of this wave, when the wave passed you, you would end up just going straight down. And we see that happening with boats in the water. That first image in the first slide that I showed you had a boat. You know, if the boat stayed on top of the wave, it would just, could never get out to sea. It would just immediately get pushed all the way back in. And again, we know that does happen close to shore, which is for some different reasons. But if we get out away from the shore where the waves are, we would just see things bobbing up and down. So what we get is we get things traveling perpendicular or at a 90-degree angle. The wave itself is moving in this direction, but the medium that it's in is going to be moving up and down. And so we're going to get this 90-degree right angle, and we get this perpendicular relationship between the medium and the wave. If we move down to the longitudinal wave, which is also sometimes called a compressional wave, we get the energy of the wave still traveling in the same direction as the other one. But where this one differs is that instead of the medium going up and down, what we end up having is the medium travels in the same direction. It travels parallel to the wave itself. And this could be illustrated like in a slinky or a spring, or if we had a bunch of billiard balls on a pool table and we hit them, the energy would move across, and it would be those billiard balls that were actually being the medium in that case, and they would be moving in the same direction. So the billiard balls wouldn't move up and down on the table to cause the energy to move across. They move in the same direction with it. And this is typically how we understand sound to travel. Okay, sound usually doesn't travel with this picture of an up and down. The air itself that I'm speaking through right now is not going up and down. It tends to be moving back and forth in the same direction as the air molecules are colliding with one another. There's a couple of vocabulary terms that go along with a longitudinal wave. One's a pretty normal word. One's one that you'll never see again anywhere else. Where the waves are smushed together, where the wavelengths get really short, that's called a compression because they are pressed. And then this word rarefaction, which I don't know of any other way you'll ever use this in life, is the opposite of that. That's the part of the wave where they tend to be spaced quite apart. A lot of people get this mixed up with a term we'll use later in this unit, which is refraction. And refraction and rarefaction are not the same thing. Very different. So some wave vocabulary that we went through, things that we want to be able to identify to begin with. We've got the crest, which is the top of our transverse wave. We've got a trough, which is going to be the very bottom part of our transverse wave. And then there's this idea of rest position, which is going to be halfway in between. So if this were a rope or something, or the ocean and the waves quit going through, that's the level that we would expect all the waves to kind of return to. If we wanted to take a compression or longitudinal wave and have something similarly labeled, the crest could be considered the compression, where the very middle part of the compression where it is as tightly packed as possible, and the trough would be kind of the middle or the most spaced out part of the rarefaction. And I guess for me, the way I want to keep these similar is if we had a boat up here, we would know it would take a lot of energy to get the boat all the way up to the top, just as it would take a lot of energy if this were a spring to be able to kind of compress it together. And then when the boat had gone all the way down, pretty much all the stored up energy would be gone, just as it would here in the rarefaction. So the trough is going to be the bottom part or the spread out part. The crest is going to be the top part or the pushed together part. Another vocabulary term we have, this one's pretty simple, it's just the amplitude, and that's going to be our height. Now the amplitude is not the distance from the top all the way to the bottom, it's the distance from the rest point to the crest, or it's the distance from the rest point down to the trough. We'll discuss the effects of these things as humans later on. In other words, if we change the amplitude, how does that change what we see, or how does it change what we hear? Another term that we have is a wavelength. A wavelength is simply the distance between 2 points on 2 adjacent waves. If we want to determine a wave, if I start at this little dot right here, one wavelength or one wave total would go up, down, that was really awful, and then back up. And once I get to that same point, notice I'm going back up the hill, and that's the same point as I was over here where I started up the hill. So that would be one complete wave. And if I started from this point, for example, if I went down and then back up, I've kind of returned to the same place. And so we would say from one point on a wave to the exact same point on the next wave. Easy way to do it is measure from crest to crest, because those are easy to look at, or from trough to trough. That's going to be the same distance. That's the same distance as this. Or maybe a little bit more complicated is in the middle, so from here to here. So from here to here would not be a wavelength, because that's not one complete wave. That would only be a half wave. The one complete wavelength would happen when we get all the way back over here. So the wave would be up, down, and then back up. So that's our wavelength. And one of the last terms here is frequency. This term for me is really similar to the word frequently, and it has to do with how often something is occurring. So this is simply the number of complete waves that are going to pass a certain point. If you were standing at the beach and you had waves crashing, crash, 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 we could do their frequency number, in other words, by the number of waves per unit of time. So we might say how many waves per second or how many waves per minute, and that would give us an idea of frequency. Well, if we got more waves per unit of time instead of crash, crash, if we had crash, 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 that's going to be a higher frequency, because the top part of our fraction would go up while the bottom part would stay the same. And as you might imagine, if that happened, what we would expect is these waves would actually probably get shorter together. They may be a lot closer to one another. And so what we're going to see here in just a minute, there's a relationship between these last two slides about the wavelength and the frequency. Frequency has its own unit. It's called a hertz, and it's the number of vibrations, or sometimes it's referred to as the number of cycles per second, or the number of waves that come past in a certain amount of time. So the higher the frequency, the more waves are going to be passing in a given amount of time. I also like to think of it as, if you could think about cars out on the road, a higher frequency would be like the cars are tailgating. Let's say all the cars are going 50 miles an hour, but if it were a high frequency, the cars would be all shoved close together and they would be coming by, whereas if it was a lower frequency, they might still be going the same speed, but they may be spread out like they should be, and they're only coming by that often. So the amount of time between each of those is kind of what our frequency is. And so finally, what we can do is, for a lot of these waves, there is a relationship between wavelength and frequency. For example, electromagnetic radiation, such as light and X-rays. So light and X-rays, they travel at the same speed. And since they travel at the same speed, what makes them different is the wavelength and frequency. And so as I was just saying, is that if we make the waves farther and farther apart, or if we space cars farther and farther apart, or if the waves are farther and farther apart, what we're going to expect is that they don't come by quite as frequently as they ordinarily would have. They come by a lot less frequently. So if the wavelength goes up, what we find is the frequency tends to go, well, not tends to, the wavelength goes up, the frequency goes down, as long as the speed stays the same. We'll compare and contrast the speed of several different types of waves, light versus sound. We'll also talk about how sound travels at different speeds in different media, between solids, liquids, and gases, and how the temperature of that might affect it as well.